Hello, good evening, both of you. So today we are here to discuss the assignment 6 questions. So we have completed half of the course by now, which is the Symmetry and Group Theory course taken by Professor Anindya Datta. And as you know, I'm Shruti. I'm a PhD scholar in the Department of Chemistry, IIT Bombay. So I hope you guys have submitted the answers. Shall we start? Yeah, okay. So the first question says, matrix element behave like a set of orthonormal vectors for reducible but not irreducible representation, reducible as well as irreducible representation, irreducible but not reducible, and one-dimensional irreducible representation. So this question for me itself is little bit confusing and I'm not sure about the answer, but I feel it should be only irreducible representation but not reducible. The answer should be B, because when we multiply two irreducible representations we get 0, and if we multiply the same, they are orthonormal, which means if we multiply one irreducible representation by itself we get 1, and if we cross multiply them we get 0. But for reducible representation I don't know whether the case is true or not, so according to me the answer should be B. Also, we can see that the GOT theorem, the great orthogonality theorem, is applicable only for irreducible representations. It does not apply for reducible. Had it been orthonormal, then it should have been applicable for reducible as well. So in GOT we write like this, right? Summation R. Oops. This is one representation and we multiply it with its complex conjugate and we get some normalization constant and Kronecker delta here. So if these representations are same, we'll get just the normalization constant, and if they are different, means if they are orthonormal, it will be 0. Is it fine? Is this question fine?
Yes, ma'am.
Yeah, okay. Yeah, so the next question is, if the order of a group is H and the dimensionality of one of its representation is Li, then the normalization constant of vectors in question 1 are normalized too. Okay, so this thing is what I have written here. This is the normalization constant. Okay, so if both are same, the this is for two representations. So if both are same, the normalization constant will be under root h by Li. Okay, so the third question is, number of irreducible representations in a group is equal to its order, number of classes, sum of dimensionalities of irreducible representation, and number of atoms in the molecule concerned. So this one comes from directly from the great orthogonality theorem, that how many classes will be there, that much number of irreducible representations we will get. So the answer is B here. Are you guys getting these? These are just straightforward questions. Do I need to explain much? Yeah, okay. Okay, so this is from GOT itself. Okay, this one is a one-dimensional representation can never have character with value. Did you guys answer this one? What character values are not allowed for one-dimensional representation? So for suppose let's take one-dimensional representation with character 1. What it means that the basis is symmetric with respect to that symmetry operation. This means okay, and similarly this -1 means the basis is antisymmetric, means the basis changes sign if that symmetry operation is applied. So the character is -1. If the character is 0, it means what? That when you will suppose this is a matrix with it is one dimensional, so it has only one element, and I have some basis which suppose let's take hydrogen atom of water molecule. Suppose my basis is Ha. Okay, I cannot take Hb here because this is only one dimensional. So suppose the basis is just Ha, then if I'll multiply these two, it means that the answer will become 0. So it means that on applying that symmetry operation, the atom goes away or it vanishes. So it vanishes. Okay, so something which will make the basis vanish should not be a symmetry operation. Symmetry operation means changing to equivalent configuration. It does not mean annihilating something, okay, or making something vanish. So this will never be a character for one dimensional representation. Okay, and also the fourth option is omega. Omega, which is an imaginary number. So this also is not possible because it loses its real significance, right? So if we apply something, some operation on the basis, it should not make it imaginary. Then the operation is not a symmetry operation. This is also not possible. Okay, omega is imaginary, right? -1 minus root 3 by 2, something like that, and omega square is plus. So both, so imaginary numbers also cannot be the basis. Okay, so for this Okay, so for this, the answer should be both C and D. But I guess this is not a multiple select question, so only answer given is D itself, I guess. But the answer should be both C and D. Is it fine? Am I clear for this question? The answer should be both. Yeah. Yeah. Kia, you were saying something? Do you have a doubt in this?
No, ma'am, it's clear.
Yeah, okay. Fine. So let's move to the next one. Okay. For the fifth one, it is the same question with for a two-dimensional representation may have a character with value 1, -1, 0 and omega. Now again, here omega is not possible for the same logic that the symmetry operation should not make something imaginary, a atom or whatever the basis is, the coordinates, it should, after applying the operation, the coordinates or the basis should not go imaginary. So again, omega will not be the character. And apart from this, all three possibilities can happen. Suppose this is a two-dimensional representation, right? So let's start with 0, the easiest one. Suppose if it is 1 0 0 -1, okay, and maybe suppose the basis is some a and b. So this representation means a stays same as a and b changes its sign or direction on applying this operation. So here the character or the trace will be 1 plus -1, which becomes 0. So the sum of off-diagonal elements can be 0, but all the off-diagonal elements will never be 0 again. So we cannot have, or maybe we can have. So suppose if it is like this, now in this case also the trace will be 0, but what is happening here that after applying this operation, whatever operation this matrix is related with, suppose then A changes to B and B changes to A. So the resultant will be BA. Okay. So this also is a possibility, and here also the trace is 0. So 0 is possible for two-dimensional representation, but we saw in one-dimensional it is not possible. Okay, now for the same logic, -1. Suppose the we can have some rotation matrix which is like this. If we have a matrix like this, then these two, if we sum it, it will become, trace will become -1. So -1 is also possible. And for 1, similarly, if I multiply this whole matrix, suppose this is for, suppose I'm just telling for example, this is not, this is matrix for Cn rotation, and if I multiply this whole matrix with a negative sign, then it will become a matrix for Cn minus. Means if it, this originally was for clockwise, then on multiplying it with a negative sign, it will become the matrix for anti-clockwise. So the trace in that case will become 1. Okay, so for two-dimensional, you can check in character table or something. You can find other examples where the trace is 1. So we can have suppose trace can be 2 as well. Suppose we have identity for 2-dimensional, here trace is 2, and yeah, like that. So for this question, the correct answer will be A, B and C, all three. Only D is not possible because this will make the basis imaginary. Okay. Shall I move to the next one? Okay. So for the irreducible representation, we have been given an irreducible representation, the Mulliken nomenclature. So we see that this is one-dimensional because the character under E is 1. Okay, so for one-dimensional representation, the Mulliken symbol starts with either A or B. Okay, now it will be, which will decide whether it's A or B, it will be the principal axis. So it, it is to confuse you, it is not written in the order, so the principal axis is here, C2. Now it is for C to Z, it is 1, which means symmetric with respect to C2. Okay, so this implies that the trace should be A. Sorry, the Mulliken symbol should be A. Okay, now you see the none of the options are A, so there should be something else to decide. So if there will be many representation under which the character is 1, so that will become confusing. So we have to make some other distinctions as well. Now the next thing which we see is whether they are symmetric or antisymmetric with respect to the planes. So if it is, see, this is, sorry, not the plane, the other axes. So this is the uh, subsidiary axis. Now it is also symmetric with respect to subsidiary axis, which is the C2 dash. Now here, so the short form to write this is 1, which means it is symmetric. Hence, if had, it will be 1, the subscript will be 1. So the subscript is 1 or 2, 1 for symmetric and 2 for antisymmetric. So the subscript is 1 here. Now the total Mulliken symbol becomes A1. Okay, next thing is we check the molecular plane or the perpendicular plane. But in this case, this plane is parallel to the principal axis, so we don't need to take this one. So the symbol will be only this much. There is no molecular plane, so we don't have to go further. Had there been molecular plane, we would have written prime or double prime based on whether it is symmetric with respect to the molecular plane. Means had there been a operation here sigma h, if it is 1 or -1, we would have added 1 prime or dash or double dash. Okay, but this thing is not there. So this should be the answer. Also, there is one more thing. If there is, for sigma h we write dash or double dash, and had there been any center of inversion, we would have written girate or ungirate. So symmetric, for if it is symmetric under I, it will be G, and if it is antisymmetric, it will be U. But those two operations, symmetry operations, are not there in this representation, so answer will be up to A1 only. Am I clear? Shall we move to the next one?
Yes, ma'am.
Yeah. Okay. Now this is the same thing. We have to find the Mulliken symbol. Now here the character under E is 2, which means it is a two-dimensional representation. First thing we need to see to decide the Mulliken symbol is the character under E, whether it is 1, 2 or 3 or whatsoever. So if it is 1, we will go with A or B and those things. So if it is 2, means it is a two-dimensional representation. So the character, the Mulliken symbol will be E itself. E means a two-dimensional representation and T means three-dimensional representation, like EG and T2G. For d orbital splitting, we have EG and T2G like that. Those are Mulliken symbols itself. Okay, so we have decided that the symbol will be E. Now what? E1, E2, E dash, double dash, like that. So the next thing we see here is this, the character under the reflection plane. Now if this is a character under sigma h is a positive number, which means this is symmetric with respect to it. Okay, so we will have is there any problem with the options? One second, guys. What are the options given? Can you tell me? Okay, there, this is wrong. Or there it is wrong. C3 it is. Here one is missing, right? What should be the answer for this according to you people? There is something wrong either here or in that assignment. So if it is 1, which means it is symmetric with respect to C3, which is not the case. It is antisymmetric here. So either it should be E2 dash. Let's leave this question. I'm also not sure. I'll clarify this in the next live session. Okay? Or if you guys can give some input. Yeah, Yeah, because something I'm feeling is wrong. Here this one is missing and the answer is given E dash. Means it is not considering the principal axis, just the molecular plane. Okay. Leave this question, I'll surely tell in the next class. Okay, I'm sorry for the confusion. Okay, let's come to the 8th question. Okay, so it is telling consult the character table of a TD point group, and for this group we have a reducible representation tau, which is given like this, and we need to figure out what are the irreducible representations this tau is made up of. So we need to break this tau into a linear combination of irreducible representation. So, and this is the favorite question of maybe CSIR and GATE exams. It comes so much in those exams. So what we need to do is we need to break in terms of irreducible representation. Now here I have attached the character table. You can see now formula for this is, how do we get it, is AI, which is the contribution of the ith symmetry operation, is given by 1 over h order of the point group summation r chi r for the reducible representation, the character under the reducible representation of this symmetry point group, and chi ir means the character under irreducible representation, which means these characters. Okay, so chi r means these characters and chi ir means from this character table characters. Okay, so ai means the contribution of ith symmetry operation. So let's start with the first symmetry operation. So no, ai is the contribution of the ith irreducible representation. Okay, so here we have 5 irreducible representations, so we will get 5 ai values. I'm sorry. Contribution of in the given reducible representation. Okay, so since there are 5 irreducible representations, we will get 5 ai values. Okay, let's start with the one. Shall I bring the character table here? Okay, we don't need these parts. Okay, so first let's find the contribution of a1. So the first representation, irreducible representation, is a1. So let's see how much a1 contributes in the given irreducible representation, which is this 15 0 minus 1 minus 1 3. So a contribution of a1 1 over h, which is the order. Now order is here the sum of these coefficients of the symmetry operation. So 1 plus 8 plus 3 plus 6 plus 6. So this comes as 24. So order of this point group is 24. So we'll write 1 over 24. Next, we have to find the character under reducible, character under reducible, and character under irreducible representation, but also we have to multiply with these coefficients. Otherwise, since suppose we are writing with C3, with respect to C3, we have to multiply 8 in it. Otherwise, we will be counting only one, for only one symmetry operation, but there are 8 C3s in this. So it's like basic math. Instead of writing 1 plus 1 plus 1 plus 1 like this, we can simply write 4 times 1. So summation can be written in terms of multiplication. So here also, since there are 8 C3s, we will have to multiply 8 in it. Otherwise, we will have to write the chi1, chi I and chi for C3 8 times. Okay. Okay. So now for E, the coefficient is 1. So let me write the coefficient. I'll be writing coefficient first. 1 into the character, the reducible representation, which is, I'm writing here, 15, 0, minus 1, minus 1, 3. So the reducible representation is 15. Then the irreducible representation under A1. We don't have to consider all these, just this row. So which is 15. Next I have to first multiply with the coefficient, which is 8, into the character in the reducible representation, 0, into the character under irreducible representation, which is 1. Okay. Next is coefficient is 3. Okay. Then the character is under reducible, it is minus 1. So I will multiply minus 1 and 1. Next, coefficient is 6. This is minus 1 and this is 1. Next, 3. Coefficient is 6 into 3 into 1. So we have completed, for A1 we have completed all the symmetry operations. So we have 5 symmetry operation, we get 5 terms, 1, 2, 3, 4 and 5. Okay, so after solving this, it will come something like 15 minus 3, this will go 0 because we have multiplied 0 here, then 6, then 18, a whole divided by 24, which is 24 by 24 equals to 1. So the same thing we have to do for all the other 4 operations. So do I need to do it or you guys will do it? You got the idea? Hello. Yeah. So do it carefully because there are many chances of making mistakes in this. So I'll just write the final answer. So for A1 I get, which I just now solved, A1 I get 1, 24 by 24. For A2 you will get 0 by 24 like this. So the answer will be 0. Okay. For E you will get the coefficient again 24 by 24, which is 1. And for T1 you will get again 24 by 24, which is 1. And T2 you will get 72 by 24, so which is 3. So I can write this reducible representation, okay, that reducible representation which is here, 15, 0, minus 1, minus 1, 3. This reducible representation can be written 1 times A1, which is A1, 0 times A2, so A2 does not contribute, then 1 time E, which is E, 1 time T1 and 3 times T2. Okay, so this is the answer. So this is the linear combination of irreducible representations which make this reducible representation. Okay, which option is this? This is first option. Okay, will you guys do it? Just while multiplying, keep an eye on the coefficient and the character. If it is 0, it will get no need to write that simply. Okay. Shall I move to the next one? So it is asking that the partial character table of C4V point group is provided, and using this character table and without referring to any other source, we need to find the symmetry of Z. Now Z is a basis XYZ coordinates. Okay, so if this is the basis, then what will be the symmetry of Z? Means when we will apply these operations, how will Z behave? Will it be changing symmetrically or antisymmetrically, or what else? Okay, so let's see. First, we need to go by operations. So like this, we will move. So first is identity. So under identity, the operation, it nothing will happen because identity does nothing, so Z will remain Z itself. So this is under identity. Now next will be C4. So C4 and C4 is applied along the Z direction. Okay, so the principal axis is along the Z direction. So when the rotation is along an axis, nothing changes in that axis. So suppose if you will see for C2Z, what we write the matrix like, okay, X changes, Y changes, but Z does not change. Okay, so the character for Z remains 1. Okay, so here under C4 also this is the same case because the rotational axis is Z axis, that will not change. Okay, you can imagine, suppose you are rotating along this 4, the Y will come, C4 means rotation by 90 degree. So Y will come here, Z will go, Z will go there, but Z will not change its place. So Y, X goes here, Y comes here, but Z does not change place. So the character for Z should be 1, and for E it is obviously 1. Okay, next is C2. Again, when it is C2, what will happen? Again, along the C2, okay, for a C4 molecule, C2 will also be along the C4. So C2 means by change rotation by 180 degrees. So Z will be here, and Y was in this side, it will go in the negative side, and X, which was on the right hand side, will go to the left hand side. So these are changing. So what I had written here, this is for the C2 case. So for C2, the character is also 1. So Z is not changing. Next thing is sigma V and sigma D. Okay. Now this sigma V and sigma D is also parallel to the principal axis, right? So suppose this sigma V will be here. Okay. This is sigma D and one sigma V will be like this. Okay. There will be two, one one like this and one along the y direction, one along the x and one along the y. So the planes will be xz and xz and yz. So since these planes contain z, there will be no change for z. So for sigma v and sigma d as well, the character will be 1. So we see for all the characters are 1, means it belongs to the mm, first irreducible representation, right? Means Z belongs to A1, which is totally symmetric representation. Okay? Did you guys understood? Okay, so how do we find in what Mulliken symbol one the basis will belong? This is how we do it. We move that basis, we apply that symmetry operation, all the symmetry operation in that basis, and we see whether the character is coming 1 or -1 or something else. And that will definitely be somewhere in the character table. Okay, so the next question is the same thing, but still here instead of z we have rz. Rz means rotation along the z direction. Rotation not along, rotation with respect to z direction. Okay, so if so how we will donate suppose I denote this as clockwise rotation, suppose like this. Okay, so this means by rz. Now if we apply I, what will happen? No change. Okay, so if we apply E, so under the identity operation there will be no change, so obviously it is 1. Under E always the character will be 1. Next one is we need to work it out from the same character table. Okay, both the questions are related. So next is C4C. So C4 means we need to rotate along this. So if I'm rotating along this, how will this rotation vector will change? Now I have to see this red curve, how it is gonna change, not this green z-axis. Okay, so I'm applying C4 on over this C4Z. So what will happen? This will move here X, this will come here Y, Z axis will remain in its place, and this rotational vector, it will not change at all because it was along the Z. So if this circular rotation, it does not matter if you change it by 90 degree, 180 degree or like that. Okay, a rotation along the z axis will not change. You understood? So it was clockwise before the operation and after the operation also it is clockwise. Okay, so the character under this is also 1. Okay, next thing is C2. Now again C to Z is the same case, so instead of rotating by 90 degree, we have to rotate by 180 degrees. So this is my rotation, and if I rotate along Z by 180 degree, so this will come here. Okay, suppose you are looking at the arrow. This arrow is there. It will suppose come like this will come like this. Okay, it was this side, it will come like this, but the rotation is still clockwise rotation. Rotation is not changing. So under C to Z as well, it is 1. Now the change comes here from this question. Now the change is with respect to the sigma planes. Okay, sigma V and sigma D. Now let's see what sigma V will do. My rotation was like this. Okay, let me join this. So rotation is like this. Now if I apply sigma plane, my plane is this plane. Okay, YZ plane. So it will reflect this, right? There will be reflection with respect to the plane, and after reflection, the rotation will become, it was rotating clockwise. Now after reflection, it will be rotating like this. Okay, anti-clockwise. Okay, is this fine? And same thing will happen if you put the plane XZ. Okay, so here what is happening? Clockwise rotation is getting changed to anti-clockwise. So character under sigma V or sigma D should be -1. It is changing direction. Hence, now E, C4, C2, sigma V, sigma D, the characters will be 1, 1, 1 and -1 and -1 in this case. For Z-axis, it was all 1, totally symmetric. But in this case, with respect to planes, it is anti-symmetric. So this representation is what? Let's see in the character table. So this is the second representation, 1, 1, 1, -1, -1, which is A2. Okay, so the rotation belongs to A2 irreducible representation. Rotation along Z-axis, RZ. Okay, am I clear? Okay. So here the answer should be C, A2. Okay. Okay, so this was for this assignment, this week's assignment, and I will solve this definitely in the next session. Okay, so this was for today. That's it. And if you have any doubts, you can ask. Otherwise, I will close the session for today. Okay. Are you all following the lectures well? Okay. So did you guys register for the exam, or you are just taking the course for the sake of learning?
No, I can't fill the exam form due to the error in the photograph upload session.
Okay, what happened? What is the error?
They did not consider my photo under the range they have given 50 KB to 150 KB. I
Okay.
have also said this in between this range, but they don't accept my photos. I have emailed that also.
Okay. Maybe you can change your photo and compress it a bit and then try to upload.
I think I have tried so many times, ma'am.
Okay, maybe there is some issue with the form itself then. Okay,
I have emailed them also, ma'am.
okay, okay, fine. Yeah, what about you, Kea? Did you register for the exam or you are just taking the course?
For learning purpose, ma'am.
Okay, okay, fine. Yeah, okay. So I will close the session for today. If
Okay,
you
ma'am.
have a
Thank you.
question, yeah, I will
Thank
explain in the
you.
next class. Okay. Thank you for joining both of you guys.
Thank you, ma'am.